Are live.
All right, everyone, welcome to another live stream community forum where, amongst other things, we field entertain questions that we receive via Discord from members of our community, but also during interrogative droughts, aka the absence of questions. We just chat amongst ourselves and discuss informal topics that don't necessarily pertain directly to our research, but are nonetheless of interest to us. So it's kind of just a way of us to hang out and have some kind of informal conversation.
So
Sometime. Mhm.
just to update the viewers that we do have a couple of topics in the background that we can suggest to have some more scientific conversation. But I want to leave the floor open for anyone to propose or suggest some direction of the conversation. Because as I say, I have a couple of papers that I've read that are interesting.
Well, Carl, I mean, to break the fourth wall, I mean, we spent a few minutes backstage or what have you, trying to find some topic, and we couldn't, so we decided we would basically just jump in anyway. Carlos, if you have something you want to chat about, I mean, I know you're often one to instigate the conversation, but why don't you just be an instigator yet again? I think
Okay, I
that's
mean,
fine.
this is more of a. I guess I would have mentioned it tomorrow more in the context of my project, but I would mention it not in the context of doing research, more of a sort of topical consideration, which is I
Mhm.
saw this talk by someone at the Topos Institute, this Category Theory Institute, and they were talking about. I think the title of the talk was something like that, something of the likes of the computer system. Where's that? Computer algebra system of the future, or something like that. Computer, yeah, yes, computer
Oh
algebra
yeah.
system of the future. Um, and it was quite interesting because so they mentioned mathematics explicitly. They mentioned Wolfram language explicitly as an example of a computer algebra system of the past in some sense. I mean, this is not to talk about Wolfram language. It's just a coincidence. But it was quite interesting because they mentioned. So there's a lot of alignment between what we are trying to do, where we've reached to this point of just basically just do rewriting on hypergraphs. We call them hypergraphs. We could say diagrams in some general sense. Nothing really changes, and that's effectively what this guy was saying. That the future of computer algebra systems looks like a diagram, sort of a typed diagrammatic rewrite system, which is effectively what we're doing. I mean, and so I found maybe not so much of a topic of conversation, but just something to throw out there. It's a nice kind of alignment of developments, alignment of sort of zeitgeist in the field, that someone that is somewhat speculating but also working on implementing some computer algebra system. They showed some implementation of groupoid theory in this system. I don't know exactly what. I don't know if it was just like a prototype of this typed system, or it was actually implemented in some other language that I was not aware of. Um, but it was quite nice to see that they referred in particular to the capacity of being non. They called it non-linear, which I think might be a bit confusing of a term, because non-linear for them is basically not string-like, right? It's when your data structures
Mhm.
go
Mhm.
beyond being string-like, and so that's effectively the whole point of what we're trying to do, right? Like that we have all these difficulties in having to contend with how matching happens, and how you parse, and how you develop algorithms that search in networks that are not even, you can't really parse them with paths, because there are many ways in which you can take paths, and blah blah blah. So I don't know. It was very encouraging to see that, and I don't know. Maybe we can all riff a little bit about what we think about computer algebra systems, and maybe more generally, I guess I can always frame this conversation in the context of, which is a conversation that I was having with Nick a few days ago, of to what degree do hardware limitations or hardware constraints and how hardware commitments in terms of our current computational environment determine the types of programming languages that we develop, and the types of sort of computer algebra systems that that we developed. Because at some point we were discussing further context for viewers and you guys. We were discussing this duality. Obviously, this what we're working on, right? A duality between tensors, typically known as tensors, array algebra, and graphs or hypergraphs. And at some point we were thinking, right, so if all these machine learning people are doing this massive tensor operations and all these complicated operations, maybe there is a way to see that in terms of graphs. So maybe there's a way to encode all those operations fundamentally as some kind of hypergraph rewriting computation instead of doing matrices. I mean, matrices are particularly efficient if you store them in typical binary sort of transistor circuit based computers, but maybe there can be other architectures that are more adapted to representing hypergraphs themselves and then doing rewrites on them without having to do all the operations on the tensors in this TPUs, like they are optimizing them now for like tensor operations and things like that. So anyway, so maybe we can phrase that more generally as how do we see the particular technological developments that have led to the current state of hardware and the kind of limitations and constraints that we have, and how there might be an interplay with the ideas that we try to put forward and how we see our work and our vision of mathematics in this context. So I mean, it's a super broad topic, but
this guy is Owen Lynch, is that right?
Mm-hmm. Yeah, the Topos Institute guy. Yeah.
Yeah. Okay, and he gave a talk at. Could you maybe summarize one more time just for my benefit, because I've never heard of this before? What's his goal in terms of computer algebra, or how does he foresee the kind of the future of computer algebra?
Well, the talk wasn't really about this is going to be the future. I mean, doing some predictions or anything like that. It was more about the sort of the desiderata of what computer algebra. So I mean, a computer algebra system is basically a programming language in some sense. That I mean, they're trying to build the computing framework, so a language and an interface and so on. And it was interesting that they also mentioned that users should have graphical interaction with the language, and they also have this graphical editor for diagrams, which is again another sort of like point of confluence with what we're doing. And so I think they are developing. I think it's Nick. I put it in. I mean, this is not related to the community forum so much, but I think it's interesting to see. It's quite short. You can go to the end. I mean, you can see this graphical engine they have, which is much more powerful than ours. I mean, because they are doing all these kind of Petri nets and all kinds of very specific things, and we're going much more general. We're just doing hypergraphs first, and then we hope to be able to implement diagrams that can represent all those things that they do, just by choosing the data structure carefully or the labeling of the data structure carefully, and then your rewrite rules carefully. But it's funny because when they present the example of a theory of groupoids, they literally say, well, these are your types, which is like declaring when the kind of hypergraph that you're going to consider, which is like us saying, let's just consider ternary hypergraphs or just graphs or whatever, and then they say, and this is a bunch of rewrite rules, which is exactly what we do. So it was interesting to see in a very different context with very different motivations that they land on the same sort of notion, where you just have to specify sort of a large class of kind of species of hypergraphs or diagrams, as they call them, and types and whatnot, or some internal structure, and then just rewrite rules on those things. So anyway, I mean, it was quite interesting to see that sort of flagged as this should be the future of how computer algebra systems work. It's like, okay, that's good. That's good to hear from the category crowd. But his talk is quite concise. I mean, it's just presenting that, saying these are he's basically saying, just to make a very concrete example for people to understand, he was comparing actually a Wolfram language expression of 2 plus 3 to something that something that is like a functorial syntax or something that is dealing with diagrams and morphisms and things like that. And he's praising the simplicity of having morphism composition as something that just rules the world. Just you just do morphism composition, which in some sense is just doing rewrite according to your rules, instead of having to parse the expression where everything is symbolic to begin with, but you're not quite sure whether this is of this type or this other type, and it's directly comparing those two things. So basically, everything is symbolic and everything is in a set, or having types and having some further structure, which is, do you operate on strings of symbols that with no further structure, or do you operate on diagrams in general, which is exactly the point that we're trying to make with hypergraphs and labels.
Yeah, I watched that video and I'm sorry.
Go ahead, Richard. Correct.
The guy actually has an interesting paper, just before I say anything else, a relational composition of physical systems. You might want to check it out. It has some very, very cool diagrams and whatnot. So he's, that's some of his prior work in a different area. I just found it whilst I was looking. Mathematica is technically kind of terms, and we sort of use head and like these sort of built-in atoms or conditions as well to which you may call like a dependent type or refinement types and so forth. So I just wonder on the hypergraph rewriting, if you don't have some sort of conditional, how you can achieve what you achieve in Mathematica with the slash colon or those constructs.
No, I don't know. Mathematica is just a tree-based rewriting system. You can treat patterns, very complex patterns can be treated as types. You can treat conditionals as some dependent types. All expression can be treated like a pattern expression can be some kind of type. You can build like a whole type system around it.
That's the point I was making. Yeah.
I was trying to ask whether this kind of language that they propose is some kind of weird dual combination of graphical language with the text language that you can just change one of those and another one is kind of dynamically updates, right? I've seen like some examples of this like this. There's a language called Enso.
Oh yeah.
Right? Before it was previously called Luna, I think. They have something like this. They said they have a nice text language, which is some kind of combination of Haskell plus Python. They have they were inspired by those, and you can basically drag diagrams around in Unreal Engine or something like LabVIEW. You can just code with just diagrams and wires, but you also can just change code and updates in both ways.
Mathematica doesn't. You said trees, but you could think of them as terms. But you also have term graphs, which allows for sort of shared nodes. So a rewrite will be, you don't need to sort of duplicate the work. So that's kind of another, Stephen had sort of decided on trees and or if you want to call them terms. But you have term graphs, and beyond that, graph rewriting, hypergraph rewriting. There's kind of a hierarchy of these, if you want to call it that, of different rewrite systems.
I think it's kind of explicitly sometimes there's some sharing, because maybe for a user, there are like expressions are all unique, but maybe in an actual like C++ level, low level programming, they actually occupy the same kind of memory. You can kind of make it work, I think.
Yeah, I'm thinking of an example. I guess term graphs just sort of deduplicate so that you don't have to repeat, so that some rewrite will not have to be applied twice. But the thing about Mathematica is the sort of side effects at every step potentially. So as you're rewriting a term, some side effect could kick in, which then affects some later rewrite within the same execution, which is kind of atypical.
Yeah, it depends what you need, what you want. Do you want like complete immutability and safety, or you just want but you still can achieve mutability in Wolfram language in a way. It's just more complicated, so that it's hidden from the usual average user. So yeah.
Hidden feature, developer feature.
I wish that I had taken a look at this beforehand. I feel like, unfortunately, I don't have anything concrete to say about it. And I haven't seen the talk, so I'm not really sure what to contribute. I mean, it's interesting. After this, I'll take a look at it. I'm not really sure what to say in real time, though.
Yeah, I mean, I perhaps was suggesting more to riff on the general idea that how constrained are we in? I mean, Nick and I are kind of fighting the constraints in some sense. So for example, when we represent, I mean, this, I think this example was mentioned before by me in some of these conversations, but when we're trying to represent an undirected hyperedge, so a bag of elements, we have to check. So currently, the most efficient way that we have to be parsimonious with symmetry operations in general is to look at all the permutations and to always consider sort of classes of permutations of collections of objects because everything is a list, right? I mean, you parse things sequentially and fundamentally you're dealing with a list. And so I find it intriguing, and maybe this is just my ignorance of computer science and computer hardware in particular, but I find it intriguing to consider, whether, I mean, to what degree is that preference in our computer systems tied to the fact that we arrange our bits sequentially. Like, it's mostly physical arrays of bits that are literally sequential, adjacent, and have that sort of tape-like structure. To what degree that is connected to that, and if at all, then what sort of computing architecture infrastructure would benefit more generalized forms of symmetry, and in particular this bag, giving bags a bit more preference. It feels like in current computer architecture, strings or tuples are given quite a lot of weight, and bags are kind of something secondary. But this, as I said, this might be just my ignorance. So I'm sort of
No. Can I say something about it? It's something Absolutely. I think about a lot, actually. Yes, sort of when I'm working sort of with low-level programming and whatnot, you always think about our design decision, because we're using this von Neumann architecture and so forth. But if you look at the evolution of computer technology from simple, digital logic all the way up to what we have now, if you look at a CPU right now, they are just massively complex, and the existence of things like caches and all of these different hierarchy of caches where because programs generally access things in very a programmer is burdened a lot of the time with like, oh well, if you have an array of structures versus a structure of arrays, then you may be able to get some benefit because you have this cache locality, and you're not jumping around in memory and causing the cache to flush all the time and so forth. So yeah, those things really do become concerns right down at when you're close to the metal. And there are many papers about graph rewriting, graph search algorithms and so forth, optimized for particular architectures for GPUs and so forth. But I have one which is really nice. Check this out. It's called the Reduceron, and it's from York University. It's a FPGA which does graph reduction. It interprets Haskell as well as a 3 gigahertz Pentium. So it's a little bit old. We're talking like 8 years old or something. But it runs on the FPGA at 100 megahertz. So what they've done, FPGA is like these programmable logic gates. It's not fixed hardware. It's somewhere kind of between hardware and software, which you can sort of reroute and program. And yeah, I mean they find their way into products. You might have one in your TV or whatever, a lot of devices, because they can be flashed and so forth. And sometimes they're used for prototyping, so you can sort of get your design down, and then you might sort of manufacture it as a specific sort of integrated circuit. But yeah, this I don't know. Sorry, did you want the link to it or something, Carlos?
No, just post that somewhere in the general
Yeah.
Discord for viewers' benefit as well.
Yeah, so it's kind of doing graph rewriting and reduction and so forth in hardware, and
What
it's
does it mean? What does it mean reduction in this context? Graph
so reduction is basically just sort of essentially rewriting.
rewriting, but like sort of okay. Yeah, I understand.
Yeah. Let me just make sure that that's
I feel
true.
for Nick. So Nick, unfortunately, will have to leave us in a few minutes. So I would actually like to hear Nick's thoughts on this because.
Yeah.
He's
Let's punish Nick's early departure by putting him on the spot for the rest of his time here.
Yeah, the floor is yours.
I'm not sure. I also kind of lost sound for a few seconds here, so I'm not even sure.
I mean, the question can be, I guess, simply put, how much connection do you think there is between the preference for ordered sequential lists or tuples in programming languages and the fact that our architecture is quite explicitly like that, at least originally, and there's like quite an architectural constraint or bias or some predisposition.
No, I'm not sure. If you want to build something reliable, it's kind of nothing. You can't really segment it, right? You have to go sequentially. As soon as you like pile up everything into one bucket, you get molecular computing or something.
Yeah.
Right?
Yeah, that's normally the example I have in mind. It's like a nice grade in a CPU, in like this silicon style, and otherwise it's like a molecular.
It's still a completely different paradigm of computing, and you can use it for to solve different kind of problems, right? But if the goal is to build some kind of computer algebra or whatever, this is a really strict mathematical objects that you manipulate, right? And you want to do some combinatorics on it and all of that. You can't really build a better architecture to support it, I guess, without doing it sequentially.
Yeah.
Maybe, I don't know. Maybe it's just I'm not sure.
Yeah. No, I think I see what you mean, and I feel your angle, because I mean, we shouldn't forget, I guess I'm saying this to myself mostly, I shouldn't forget that sequentiality is the best model for time implementation and process, right? I mean, at the end of the day,
yeah.
When you actually do things in process, they happen sequentially, at least in sort of one stream of activities. Of course, it's
like the sequential or very controllable parallel computation like we have in the modern computers, right?
Yeah.
You still can do parallel, but it's still very controlled in a way.
Yeah, you need a lot of synchronization if you have things that potentially can overstep each other and things. So you have to enforce these ordering constraints, which sort of essentially forms relations like this must happen before or happen after some.
I would argue, and this is going really to the core, and in a way, even giving a segue into another topic that was discussed in the Discord recently as well, which is, I would argue that the fact that we are live here having this conversation, life, biological life, is an example of computation that does not use the digital architecture, right? I mean, we're at the bits in biology. Sure, in the memory part, yes. I mean, DNA, RNA, yes, there's something digital going on, but I think everyone agrees that there's way more computation happening than what's on the tape, in the sort of acid, nuclear acid tapes, and I think that's kind of close to this idea of sort of a non-digital architecture, and perhaps you can argue that it's way slower somehow, and compared to for some things in some regimes is much slower than digital for other regimes, but on the other hand, it seems to be much more powerful in some sense. It seems to be much more universally flexible, and yeah, I don't know. It's interesting. It's that kind of boundary, and then obviously when there's the question of universality, and I've had these conversations many times with some friends who work in mathematical biology, because there seems to be quite a strong results of universality, meaning that the concept of universal computation right now seems to have the mathematical concept, which involves potentially infinite things, seems to really stand its ground. It seems to, it doesn't seem that you can do some other kind of computation with, say, molecules or proteins, or doing with shape and things like that. But what it also seems quite obvious is that even though you can universally recover that computation, I mean, you can always imagine that you can build a simulator, right? You can build a sufficiently sophisticated simulation that runs on sort of digital logic, digital computation that will effectively reproduce the phenomena that you want at the resolution that you want, right? I mean, that's kind of an argument to say that, yes, okay, so you can do this very big digital stuff, but that doesn't mean that it's the most efficient, right? It's likely that there will be non-digital computational frameworks that are much more efficient and much more adapted to certain situations.
Analog computation.
Analog computation. Yeah.
There's like Shannon's general purpose analog computer, and then there's the whole relativistic computation, which is a more theoretical idea that send a computer faster than light or something, or to infinity, and you'll get your answer and so forth. But,
I did want to share. I just put it in the chat. I had a meeting with someone recently who's kind of interested in the institute, who's right now a postdoc at Rockefeller, but he has a contention that some of RNA behavior might be either similar to combinatory logic, or at least can be modeled well with combinatory logic. So, and he was explaining to me, I won't dare to try and summarize what he was saying, but he was suggesting to me that if we can better understand, if we can develop a better computational model for RNA, it could help to explain all kinds of things like the quote-unquote non-coding sequences, and better understanding the development of cognition, et cetera, et cetera. So, I don't know. He's someone, if we're interested in discussing some of these topics and the relationship to computation, this is someone who's kind of actively working on it right now. So we could maybe we could invite him to a community forum. We could discuss some of these topics in greater detail. Because I've met him, and he's a bright, interesting guy.
Yeah, I mean, and that's commenting on the particular research here. If you understand the computational framework that RNA gives, so whatever kind of computation is running on the RNA substrate, I think there's a wide chunk of the Origin of Life community that believes that that's the main problem to solve. That you need to figure out how, when you get, it seems fairly plausible that RNA molecules started forming in some conditions, and relatively long RNA molecules started forming, and so it seems to be a problem of solving the kind of computational landscape that these molecules will enable. That you go from just kind of a prebiotic RNA generation, kind of more or less random, to having evolving life at some point. And I find that very enticing, because, to be honest, having read about what the options are, this so-called RNA world origin of life hypothesis seems the most reasonable to me. I mean, it seems that proteins kind of evolved from RNA, and RNA was doing kind of a protein-like. It was kind of a in between DNA and protein function before there was any kind of cellular structure or separation in enclosed organisms or anything like that. So I don't know. I find this extremely fascinating. I think this is, as I said in I think a couple of community fora ago, this is really the frontier that is our understanding, and I think we're getting there. We are slowly realizing the what seemed like an analogy to me a few years ago, and I guess to the community in recent years, has become not so much an analogy, but like a fact. It's almost like, yeah, this is not just analogous. That's what's going on. I mean, what goes on in your computer and what goes on in in a nuclear cell, that's basically the same thing. It's like the same phenomenon is happening, just different substrate, different kind of software hardware relation going on, but essentially the same phenomenon. I mean, this was realized many years ago, of course, but it's. I think we're coming to the point where this is operational and kind of within reach for testing.
Or at the very least, that models of abstract computation are surprisingly effective in helping us to understand this. This is still something that I grapple with, and it's a question about which I do adopt a pretty conservative stance. Is like, what is computation? Are we going to describe all processes as being computation, or is computation, are these more formal theories that we've developed, and then we are kind of projecting those onto observables, or kind of empirical results or epistemological topics in order to understand them better. Because as soon as you make the claim that basically things are computation, we addressed some of these questions like every single stream. But as soon as you begin to ask those questions, I think that I think at the bedrock, there are some questions that are raised, I think become quite difficult to answer as soon as you just say that things are computation in general.
Yeah, this is a question that, I mean, it's come up several times in many. It's kind of a classic of the community forum.
It's a classic.
This point.
Yeah.
But it's a good classic. I mean, it's a question that, I am quite torn between saying something like, oh yeah, any process is kind of pre-computation, if not computation itself. And it's like, sure. But on the other hand, you have this fact of almost computation recognizing itself, right? It's like, many times when I talk to biologists about life, the kind of point of the conversation where we kind of disagreed is that, to me, life seems, what looks like life is what life looks to itself almost. What does life look like to itself? It's like if you, a rock is not wondering what is life, right? Only life is wondering what is life. So in this sense, I can extend it a bit more and say that, I know what computation is, and if I look phenomenologically at the universe, I see that what is going on in what I believe is my flesh hull is similar to what's going on in a computer, and similar to what's going on in other systems. And so I think, right, so it's that kind of phenomena that is kind of recognizing each other, right? It's I don't know. I'm torn between, it's something very universal, very fundamental to it. Just when it expresses enough, then it can recognize itself, and that's what you call it. But of course, I don't know. I mean, which would imply that there's only a certain type of states that are computational, and perhaps this is more related to sort of thermodynamics and ergodic arguments and things like that, of arrangement of systems and things that I don't know about, basically. But yeah, it's a question that I'm torn, and I have to say, I've talked to people that are quite knowledgeable about this stuff and are doing research on these things, and there's no consensus. I've not heard I've not heard. Oh yeah. This is the picture, and we're all kind of agreeing that this is the way to go. There's by no means like a form view of what computation is, and so this is it. This is what computation really is, and just go out there and find it, right? I mean, it's so yeah. It's a good question because that those are the good questions, right? The ones that, but they are very unsatisfying for a scientist because it's almost like consciousness, right? It's like all these kind of, it's all these C words that plague our science and philosophy.
Well, I think it does draw one's attention towards some of the most outstanding and vexing questions in science, which I think ultimately pertain to the possibility of there being some sort of a divide or a gap or a gulf between our own ability to construct models and theories and explanations for things we happen to see and whatever that thing is itself. And as Carlos brings up, in maybe this kind of Kantian way, there's also this kind of impossibility of us really understanding outside of our own sensory faculties what there is. Of course, these are basically platitudes, and this is like a classic problem in philosophy. But as soon as we then take, say, some perhaps contemporary either technology or formal theory, and we say, okay, on the one hand, this is quite useful for helping us to understand things that we see in the world. That's one thing. As soon as we begin to make kind of prior commitments, say ontologically, that is the way that actually is the way that things are. Like we happen to come across this theory because there's something fundamental about it, and whatever this fundamental essence is, it also happens to kind of permeate across just everything that we see in the world, even though we are only humans and we're machines, maybe, or we can think of ourselves as machines. That's the whole point, and we're just processing sensory data that we receive. I mean, that's the question. Is like, do we just want to think of theories and models that we produce, science that we do, as helpful for approximating or making sense of the world, or are we going to try and kind of like project it back and say, no, like this is not even a matter of science. We really think that this actually is the way that things are, as opposed to this is just what we think we know about how the world works. I don't know if it's abnormal or not, but I think basically no matter how much I learn, I'll always take the former approach that I don't really mind the discomfort of presuming that we really will never have any kind of absolute access to the world, and we're always kind of just making guesses or trying to approximate or trying to guess. Now, where mathematics fits into that is another question, because on the one hand, you're creating models, you're creating formalism, you're engaging in abstract thought in order to try to capture or tame or explain things you happen to see using some kind of formal machinery. And then mathematics is like, okay, let's just forget about explanation altogether and just work on the formal machinery. And that's yet another kind of deep question. Like, does that say something about us and our own cognitive faculties? Are these things kind of Platonic objects in the sense that if you had some completely different organism that had a completely different physiological makeup and was on a different planet and the chemistry was different and the evolutionary process was different, would they still come up with Hodge theory, or p-adic numbers? It's not clear. Sorry, just so that people know, I'm doing a radical readjustment of my sleep schedule. So I've been awake for maybe 24 hours or so. So the best thing I can do is rehearse classic questions in philosophy, which is not fresh, but I don't know, maybe for some people it's a useful reminder.
No, but I think that's very interesting. And mathematics, I have an intuition that mathematics is kind of the smell of computation almost. You know, it's like the I know that's a weird metaphor, but it's almost like, you know, we are the users, we are near the machine, or we are the machine ourselves, and you know, and so we get to, you know, experience firsthand what computation is like. And I think, by the way, when I say mathematics, I really mean any kind of language that has some sort of grammar, or some kind of systematic meaning making kind of communicational system. So anything that a lot of things will be called mathematics with a definition that typically aren't, but mathematics are certainly within that class. I think traditional mathematics are certainly within that class, and I would say that it's almost like, maybe not the but like the noise of the computation running, right? It's like you have these computational entities, and they kind of make noise, and that noise is what you hear as mathematics. Like the user hears it as mathematics. And I mean, I think there's a good point to or there's credibility to Platonism or Neoplatonism in that at the end of the day the origin of that noise is more or less unique, you know, from a materialistic point of view. I mean, if you just say whatever there is in the universe, that is giving rise to this noise. Obviously, the noise is going to be different in some ways because how it's produced will make different kind of sound, but fundamentally is coming from the same place somehow, right? Like everything is. I mean, this is somehow surprising, right? In the universe, when you're born into this universe and you realize that there's such thing as a periodic table and there's such thing as, you know, only a few interactions, and it's not like you're constantly getting new information that you're. I mean, I don't see a reason why we couldn't have like a universe where, you know, every day there's like a new fundamental force and it's just things are just going. I mean, maybe there's an argument about stability, but you know, there's certainly it wouldn't be a zero probability of that being stable enough for us to exist, right? With the known laws of physics. So I feel like that is somewhat surprising, right? I mean, the fact that there's this kind of uniqueness to the universe, it's somewhat surprising, and that is so. That's why I attribute some credibility to Neoplatonism in some way. Like I wouldn't take Neoplatonism as, you know, whatever I'm dreaming of, whatever I'm right now visualizing, that is actually sort of accessing. I mean, that's to me going a bit too far. I respect them; it's fine, but for me personally, that's a bit too far. But I do have some sympathy for the feeling that eventually, because the substrate seems to be scientifically seems to be quite unique, and by unique I mean this stable kind of conservative, right? I mean, the universe is quite conservative in a way, right? Like energy is conserved, like things are, you know, you can break. I mean, we have a lot of no-go laws, right? Like we don't know the details, but we know that this is going to be preserved. It's quite a Hamiltonian universe in this sense, and that to me justifies a bit or gives some credibility to the fact that whatever happens as more emergent and more mind-like from systems in the universe, then shares common patterns because they are stemming from the same quote unquote ontological place, right? So, so yeah, that's
why do you think that the uniqueness of, say, one particular universe, why do you think that strengthens a Platonist position or makes you more inclined to take that position?
I mean, what I think strengthens or makes Platonism a bit more credible in a way is the fact that we scientifically observe the universe to be quite stable at the fundamental level in some sense. I mean, we observe fundamental physics. We have things like a periodic table. We have we have a lot of regularity in some sense, and maybe deep down at the quantum level, we do see some sort of generation, right? Like there's some kind of things are being generated, things are collapsing and sort of fluctuating and things like that. But they happen within shells of constraint, right? Like there's randomness, but it's very bounded, right? Like these things, and to me that gives this notion of stability, or call it.
I see.
I see.
So
yeah.
So there are physical conditions that have to be satisfied in order for there to be any kind of physical or material permanence. You need something like that in order to begin to have anything like an abstract object, right? If the universe was in complete flux all the time, it was chaotic and nothing was preserved, why would I have some concept of a house? I have a concept of a house because I've seen houses day after day after day. They're more or less the same. They look the same, and so for instance, I don't have any conceptual, abstract understanding of anything that I've seen that's been highly ephemeral, unless I can attribute it back towards something that's been relatively constant.
So it's
right?
not so much. It's not. I mean, that's one reading, but it's not so much that. But because you could be in a pocket of in a pocket of stability and
Meta-stability.
and some kind of pattern repetition, right? You could be in that pocket, and you could see many houses, and it could still be, viable for you to develop this pattern recognition of and repetition of houses, right? I mean, but
Sure.
to me, but if the universe, if that was a likely fluke, right? So you had experienced, or you had several instances of, oh yeah, I went to this other part of the universe, and suddenly the concept of a house doesn't even make sense because the laws of physics don't even apply in the same way that they apply over there, right? Like meaning that you have different periodic table, you have different fundamental forces, things like, I mean, it's kind of stupid to say because it's kind of counterfactual of what we can experience here. But my point is, because it's a counterfactual, it's kind of absurd. That's why Platonism, I think, is a bit more credible, because the universe seems to. I mean, it's this kind of surprise that I always say to everyone, like, having studied physics for many years since I was very very young and eager. Like, the most surprising thing that has happened in all these years of my study of physics and mathematics is that the universe seems to know about mathematics in a way that is absolutely surprising. It's not so much that mathematics is good at describing the universe. That doesn't surprise me. It's what kind of mathematics happen to describe the universe very well and how we found it. That is what is very surprising. Because, you see general relativity or quantum mechanics and these kinds of things. And it's not so much that they are weird. It's the fact that, they were never developed for that purpose. And they happen to fit very, very well, to the point where, we've spent the last 50 years in high energy physics and string theory kind of stuck because they are just too damn good. Like, it's like, yeah, these are exactly the mathematics that we need for this kind of stuff. So that sort of scientific fact is what primes me to take Neoplatonism a bit more seriously and to give it a little bit more ground, because it's not only to, I mean, the usual argument for Platonism is based on some argumentation. It's like, oh yeah, because if I can think of these ideas, it's kind of made of logic, it's made of words and arguing, right? I don't buy that. I don't get convinced simply by some, if I were in Greece at the time and it's like, oh, sure, whatever, I'll probably go and fight in some war and die and whatever. Like, I wouldn't be thrilled to be in the academia and just discuss stuff with words. But when you show me all this experimental evidence and measurements of light bending and black holes and quantum phenomena and discovering particles and all this kind of stuff, that is not made of words. That's not made of argument. There seems to be very deep fundamental patterns that are very consistent, right? And that's what I eventually go for the regularity that will manifest itself somehow. It's not a necessity, but I imagine that if you're made of the same stuff and that stuff is very consistent, it's very sort of self-consistent, then the kind of mind-like ideations and dreams that will come out of that, like in our brains or in computers or other animals or whatever, they're going to share something fundamental and universal because they come from the same stuff, and that stuff seems to share a lot of universal stuff. I mean, there's such a thing as a law of physics, and we still have laws of physics as a very powerful thing to describe the universe, right? So anyway, that's kind of the summary of an improvised kind of argument of why. But
yeah, I guess my take on it would be, it's astounding that we've been able to, through our encounter and our love affair with mathematics, we found that it's so plastic and flexible and expressive that we've been able to develop theories and frameworks that where you have conditions, you have properties, you have objects. They're so precise. If you change them even a little bit, the statements are radically different. And so we have this machinery that's so acute that we've actually been able to develop models and theories that match, our empirical experience of the world. And there's no reason inherently why we should be organisms that have both these empirical faculties and these kind of faculties of reason. So I guess one way of thinking about it is it's so miraculous that we can do that Neoplatonism is maybe, if nothing else, kind of a celebration of this capability of ours. And if people, have ideas of objects and they see that these objects match really well to their kind of empirical experience, so well that you might want to entertain some kind of collapse with the two or some very strong relationship between the two. The fact that people can credibly do that, the fact that you can credibly be a Platonist and you can be high functioning, et cetera, I think that's what's quite interesting. Because you can imagine if math, what I mean is if mathematics was really coarse and a blunt instrument and not very good, or our mathematics was very good, but our empirical faculties were inconsistent or inaccurate, I think it would be harder to be a to be kind of a Platonist, because either we would see things, we'd have no means of explaining them, or we would be very good at in the kind of the formal realm, but our own kind of empirical vision of the world would be inconsistent. It would be very hard to, we just wouldn't have very good empirical observations against which to compare our own formal thoughts. The fact that we have both, I think, is what gives us this kind of confidence to think about things that we encounter in the world as being these abstract objects, because we can kind of marry our own faculties of abstract reasoning with things that we happen to see. And the fact that we can do both of those well, I think, means we can be quite high functioning Platonists. And the fact that we can get away with that, I think, is pretty cool.
But
as Carlos is suggesting, if the world was even slightly different, we wouldn't be able to do that.
Yeah, but I'm a bit confused. What do you find miraculous that we can use mathematics to predict the world? I missed that part.
Yeah, I mean, the fact that you can imagine some worse human that could, you can see things and you can hear things and you can feel and you can touch, but you have no abstract reasoning for thinking about, the world at all. You have faculties of vision, but you're not, maybe you're not even thinking over time like this is a desk or this thing's a modular form. They're not becoming these kind of abstract objects, let alone abstract objects that could then fit into something like a rigorous mathematical framework where they become highly manipulable and you can continue to specify their properties further and further. So the fact that we have both these empirical faculties, which are just specific organs that we have that feed into our nervous system, and the fact that we have these faculties of reason that allow us to develop complicated frameworks of them, and the fact that they happen to be quite compatible, so that we entertain quite sophisticated exercises in physics, but then they happen to have predictive power, like mathematical exercises in physics that then happen to have predictive power. That's what's quite miraculous, right? You go down some very deep line of thought, say in Lie theory or something. The fact that you can then find on the other side of that something that matches the real world is on the one hand,
effectiveness.
Yes, it's the unreasonable effectiveness of math, which I'm basically saying is, it's something. But we have some faculty of reason, for lack of a better term. We're also quite good at observing the world. We could be better, but we're not bad at it. And the fact that we both, can kind of sense things about the world and think about the world, and these things actually seem to correspond often. Is I think that's the thing that's miraculous, because you can imagine a situation in which you have one or you have the other, but they don't coincide well.
Yeah, no, I would say this is the unreasonable effectiveness of mathematics, but it's but it's also the fact that the example you used for me is the most shocking one. Is Lie theory being developed at the end tail of the N-Largen program, and differential geometry in the 19th century, which was almost purposely this hyper abstract mathematical program of like, okay, we've broken with Euclid, we've broken with this kind of stuff, let's go, we found projective geometry, how many other geometries are there, let's just find them and let's go, right? And these are abstract algebraists and geometers inventing all this field, and then 20-30 years later you go out, you go to your nuclear physics lab, and they're like, oh, so yeah, we're observing some blips here and there, and they seem to arrange. Wait a minute, this arcane diagram, the root diagram of this SU3 representation, and happens to match the mass spectra of this part. Like, this is just surreal when you think about it. I mean, because there's a component of luck, historical luck, that, what would have happened if we didn't develop Lie theory 3 years earlier? Right? Again, this is always like in my mind. It's like, what if for some reason mathematics went in hardcore into number theory, and much more algebra and category theory took over, and all those geometries were not really explored to the point where, at the time that we are discovering these things, they are not really fully developed. And what would have happened? Because we wouldn't have gauge theory, right? So I don't know. It's kind of it's this sort of very deep surprise, and at the same time, and this may be to reinforce many of my points in many of the conversations we had at the Institute, is because I see the very specifics of history being so relevant for the status quo of physics, that I normally take the view that that's just an accident, and it's a great accident. It's a very powerful theory, and there's nothing wrong with it, but it's likely that other mathematics that were underdeveloped could have very powerful ways to describe things that we still don't even see, because we don't have the language to speak about it, right? So to me, that gives on the one hand, it's very spooky to think of like, oh wow, how in the world did this happen? But on the other is like, so all the mathematics that we didn't develop properly could have similarly powerful effects in descriptions of nature. So it's creepy on the one hand, but very hopeful and motivating on the other.
But it might sound vulgar if I say this, but my view at this point is the world's very complicated. The more complicated we make mathematics, the higher the probability that we will find that there are more things about the world that we couldn't explain before that we're able to capture now with new mathematical formalism. That's my kind of view of it, is the finer we can make the mathematical instruments, the more likely it is that it can just perfectly kind of capture the world that we see.
Yeah, for sure.
You used this term once, Carlos, I think called Platonic justice. So just to kind of go full circle, my own, which is, I think it's completely different from what you were saying, but I think my own kind of notion of Platonic justice is that mathematical labor with time is rewarded in a kind of an empirical way. Like, the more you invest in these tools, the more rarefied and refined and flexible and precise, where you're doing something precise, but it's something precise that you haven't seen before. I think, and if it's well understood across the mathematical community, so it doesn't die in a well somewhere and not be utilized by other people, then I think the higher the probability that you'll find some particular kink about the world that happens to be poetically explained by your new gadget.
Yeah, indeed. So Hussam just asked the question on YouTube. So
wow.
I suggest.
Oh, we riffed long enough for Hussam to come and ask us a question.
It's been lively actually in the chat. But I suggest the following. I suggest it's completely related to what we're talking right now. But I suggest that, because we're coming to an end, I read the question, and each of us here give their thoughts, and we close on that. Okay? So Hussam Ismail asks, most modern theoretical physicists are differential geometers, in my opinion, with the stark exception of you guys. I think that's an overstatement. There are other people who are not us that are also not theoretical physicists, but we take the compliment. And he asked, do you believe other formalisms would work to describe the world? to be clear, do you think we would have had so much success? So maybe Richard, Lucas, go first, because James and I have been riffing on each other for a while.
Maybe something about Langland's program can say something about that, no? The equivalences. Yeah, Łukasz, over to you.
Yeah, maybe you have all these sorts of geometry to algebra, the world it is, and the other way around. And there are attempts to actually construct physics using like abstract algebra by algebraizing these geometric structures, like non-commutative spaces and this sort of stuff. So maybe yeah, like, but in the end, it all really seems to be the same. You can model algebra geometrically, and you can model geometry using algebra, really, if you try hard enough. So I don't know. In that sense, it seems to be one word and just different languages. I don't know if we could start with algebra. You know, at least for
I think we could.
at least
Definitely.
for me, my intuitions are more geometric. Even when I think of algebraic objects, that I'm not just shuffling symbols around. I just have some geometric picture in my mind. So
Yeah, I am the same actually. Just to follow up your reply, Łukasz, I think geometrically, but at the same time, I think that formally you could start pretty much anywhere, and particularly you could do. There's this approach to. Some people have called it algebraic quantum field theory or formal quantum field theory and things like that, and I mean you don't. I mean geometry is secondary. I mean, it's not even important what kind of structures you have. It's only important that you have. I mean, it doesn't matter if you call your things rings or manifolds, or you know, if there are coordinates or there's variables, or it doesn't really matter, because as long as you have the right sort of categorical structure and sort of landscape of connections, seems to be enough, right? So yeah, it's been a beautiful few decades, I would say, in the last few years. Like all the progress that hasn't been made on the front of fundamental physics in the more traditional sense, I think has been made in the front of formal and rigorous charting of what physics is about, really. And you know, I humbly, I think, contributed a little bit with, you know, some notes of what people have done, and you know, in all this talk about, you know, how Hilbert categories, or categories that essentially look like Hilbert spaces, are essentially what we are after, and you know, symplectic categories quantized to Hilbert, and how all this is one big language that you can, if you want to think of symplectic groupoids, that's like a general object that encompasses everything, you know, in this traditional way of doing this. I don't know, and of course all these formalist, TQFT kind of people that have these very categorical, abstract approaches to physics. I mean, this is very different from what the critique to that sort of school of mathematical physics. I think it's quite different from the usual critique that people address to string theorists, right? Because in string theory, it's mostly sort of continuing from the tradition of theoretical physics, but with a lot of new machinery from, you know, sophisticated mathematics, is trying to essentially do the same thing in some sense. This other thing is more about, you know, you take all that as data, and you try to chart what's going on, and you try to characterize what is a physical theory, what are the ingredients for a mathematical theory to be a physical theory of any kind, right? Regardless of the particular interactions you want to include, regardless of fit to experiment, but what are the conditions for the theory to be able to be a physical theory eventually, right? I mean, and these are the things that have been developed in the last 20, 30 years and still are ongoing. I mean, there's a lot of people working on these things, and it's been quiet because it's not flashy, it's not advertised, you know, there's no big revolution happening, because it's mostly sort of tidying the room after the string theorists and theoretical physicists kind of run, with things. But yeah, it's quite nice. But anyway, Richard, I think we should all try to answer.
The thoughts that were popping through my head just there were like thinking about the sort of the infinite limit of some sort of mathematical process, and perhaps that is actually what we're sort of the reason we find mathematics sort of can be transposed onto our observations so well is that the physical universe has, in a sense, sort of explored all of mathematics. And that's maybe a bold thing to suggest, but thinking about sort of the infinitary and all of that, that if you took some process, some rewrite process, or something which is essentially growing mathematics to its infinite limit, then any mathematics would find itself somewhere in the physical universe, and any organisms within that universe, no matter what they invent, they would find some way of applying it to observations, because it's essentially sort of all manifest somewhere. But you can call BS on that if you want, but that's my thought. So, yeah. What would it look like to grow mathematics from some first principles, and take the infinitary object of the resulting infinitary object that you obtain?
Wait, what is the question again? What would it look like to do exactly what?
So if you were able to sort of grow mathematics from first principles and then obtain some infinitary object, then you would find that any mathematics you invent is sort of present in this thing. So to me, that's why it's sort of not surprising that most things that we do, we can find an application for it in the physical world. We can always find some situation where you can map this mathematical system and it has applicability somewhere, and then it's my sort of like thinking or theory or postulation that essentially what we're living in is some sort of like infinite limiting object of that. If you were to continue our mathematics forever with human beings thinking and developing it into something more and more advanced onto infinity, that object that you yield is sort of like the maximally powerful or maximally complex. I mean, it's you can't sort of conceive what that thing would be. But to me, that's kind of the floor for our sort of physical reality.
I kind of have a bias where, you see, I won't be surprised to learn that there are, say, certain mathematical objects or relations that where we can't find anything physical that they can usefully describe. But in principle, you could imagine maybe some other universe, or if we're in some landscape, or it depends on the setup that you have, that it could describe something somewhere. So when you take that kind of view, and I'm not making this as a claim; it's more of a confession. But I tend to harbor this presumption that mathematics is more general than physics, and that your physical empirical observations of what we call physics are kind of instantiations of things that can be described well by mathematics, but that if we're kind of maximally creative mathematically, we'll find that many of those things that we develop are useful for the real world, but maybe not everything. Though,
but the other way around, the other way of looking at that is the physical universe has enabled us to conceive of those things. So essentially, it's more general, because it's providing the kind of, the petri dish in which we live, where we can now conceive of these mathematical objects. Without the physical universe, we couldn't do the computations to even find those things and carry out the mental processes in order to, for example, even just logic, Boolean logic, or those kinds of things. Like, it's like,
Yeah, but now is where the Platonists would enter the conversation and say,
yes. Well,
if you're actually
uh-huh.
moving in an orthogonal dimension that is like not part of material reality, then Like I'm just playing the Platonist advocate here. I'm not I'm not
Yeah, sure.
being Platonist
Yeah,
myself.
yeah, yeah. Well, yeah. If you count the thought itself as a physical instantiation of the thing, then there'll always be a one-to-one, or at least
That's
at
an
least a
interesting thought.
one-to-one correspondence, right? I thought we were considering the question of, other than just the thought of it, do we find that it'll model something else in addition? But it's a very good point, which is like Galois groups, you know, someone did have to perform the computation that gave rise to them. So it's at least one example where it's in the real world. On this question though of this question that was asked to us about, you know, do we think that there are other formalisms that can apply? I mean, I don't know if this will be unexpected or not, but you know, with time, my view, I think it's akin to Wukash's view, which is even if our prowess in describing the world, you know, improves and improves with time, I think that there will be many models and formalisms that are not only accurate, but I think with time we'll find more dualities, punctorialities, correspondences, and there's something about that I really like, in part because it gives people choice to some degree. You can be versatile, and you can transport something you're thinking of across some, you know, these different correspondences, and you approach something this way when you want to, or this way you want to, or this way that you want to. And I personally really like that. And so, unfortunately, I think at the moment, due to reasons that I think are partially political, partially due to the way that we've kind of structured social media, which I also think is not very enlightened. I think there is some kind of reward at the moment for this kind of factionalism within, say, the sciences, especially within physics. And also, there's this kind of thirst for unification. And I think both of those are kind of misguided. Like, I think it's much better if we have some sort of pluralism, where, like, we know fine well, with time, as we get more precise or as we get more abstract, we'll likely find dualities and correspondences and opportunities for transport between different ways that people are thinking about them. And that's good. It's good to accommodate that pluralism. It'll mean that more people with different backgrounds who think about problems differently will still be able to do good work. And I think that that's kind of, you know, it's like ontological democracy plus exchange, which I think is very good. And also, I presume that things will get more precise, they'll get more fine. Finding how things relate at a finer level will become more difficult. With time, we'll also find how things relate on a higher and higher level, which will be less. It'll be more abstract, but it'll be beautiful in a kind of in a less concrete, but in a way that subsumes more under these kind of taller concepts. And personally, I don't know if it's a cultural thing, but I'm looking forward to much more to kind of pluralism, different approaches, finding the correspondence and the syntheses between them, and digging deeper and also climbing higher. Digging deeper in terms of detail, climbing higher in terms of abstraction. And I just presume that that's gonna continue indefinitely. And I think this notion of we're going to find some unification. This unification seems like this kind of postmodern messianic event that I think is maybe we should disabuse ourselves of it. Like, is there really going to be this single point where we have absolute knowledge? To me, it's almost this death wish in science. Like, we want it to come to an end. Not to get full Lacanian or anything, but it's like I think enjoying the process of science itself, instead of having some kind of, you know, terminal state where we think it will come together, and also accommodating greater plurality, I think is quite important. And it's not at all clear at the moment, by the way, how things like physics and math are going to relate to each other. Of course, a lot of work is done on that, but there's still a lot of controversy in terms of how math and computation fits together. That's becoming increasingly clear through constructivism. there's this kind of other relationship between computation and physics, which I'm ardently suggesting should just be, kind of constructivism in physics, which I think is highly underdeveloped. That's quite interesting, and it's going to relate to the relationships between math and physics and between math and computation. So there's a lot of work to be done, but I'd recommend reducing the kind of gang warfare in the sciences and just trying to create a scientific community in which we're doing more to find the relationships between different theories and models, et cetera, because I think mathematically, once you get into contemporary mathematics, you find that there are dualities and correspondences and transports and isomorphisms basically just everywhere. I think this is the context in which Carlos actually introduced Platonic justice. I think Carlos is basically saying if you find these isomorphisms, these correspondences all over the place, there's something kind of just about it. Carlos can maybe explain that better. But yeah, that's my take on plurality of approaches and unification and kind of future of what I think would be a good, healthy scientific community.
Well, that sounds like a great epilogue to me. It's very timely and very appropriate.
By the way, folks, this is a modular form, and this is something that you can encounter in the Langlands program. And the reason why you're seeing this is that I recently moved the desk in my apartment, and I did that, but I didn't clean the apartment, so I only did one of the tests, and so that's why you're seeing the modular form in the background. The mess in the background does not have these nice symmetry properties. And later, when I pick up a broom and I apply a Hecke operator to this, it's not going to stay invariant at all. All right, guys. Well, I didn't know if I was going to survive this, given that I've been up for over 24 hours. But this was fun. With time, I'm building confidence that we can basically just hold these community fora without any idea of what we're going to talk about, and we'll naturally gravitate towards interesting ideas. Hopefully, other people find them interesting.
Yep, I think the chat was quite lively. I think people were, saying positive things.
Cool. Well, everyone, thanks for watching, and we'll see you tomorrow for our roundtable. We'll be discussing research that we've been doing, so slightly less philosophical and whimsical and more concrete. I'll have gotten some sleep by then, and probably So anyway, hope to see you then. It's at 3:00 p.m. Eastern tomorrow.
Yep.
And thanks as always. And if something that we mentioned or we discuss, piques your interest, or you're thinking about it more, of course, we're happy to hear from you. If you're embarrassed to post something in the Discord because you have a question that you think is elementary, or you're having trouble posing the question, or English isn't your first language, you can always just message us privately. We're perfectly friendly people, or at least 4 of us are, and you'll have to guess which of us is the unfriendly one. I'm just kidding. I don't know who they would guess. We're all really, really friendly. Anyway, so you can do that too if you don't want to post publicly. I know what that's like. So anyway, thank you all, and see you tomorrow.
See you tomorrow,
Cheers.
everyone.
Bye-bye.
Hey.